Yes, my name is Charles. I work at Woven by Toyota, and I'm here to talk a bit to you about the first component of Arene that is being open sourced. And this is Arene Base, which is our fundamental C++ library. This is going to be a slightly technical talk. I'm going to have some code on slides, but it's not going to be super C++ heavy. So I'm more going to talk to you about what you can do with Arene Base rather than getting into the details of how to do it. So please bear with me. So the first part of the pitch here is we have to talk about what is Arene Base useful for. So I think the first use case is real-time safety. I think probably a lot of people in this room have been in situations where there's some nice class maybe that you would really like to use, but potentially it could throw an exception or do a dynamic allocation or something, and so that's not real-time safe. A lot of sort of general purpose open source things are in this situation, which is why we have AGL, right? To sort of think about narrow down from general purpose open source stuff into automotive specific stuff. Another nice use case is you might have this problem where you want to be using more recent C++ standards or other types of things. I just happen to like C++. But you have some weird tool chain or these coding standards that are keeping you on this very old version. So you might want to use C++ 20, 23, 26 just came out. But you're stuck on 17 or even 14 because that's all that the environment supports. This is less of a problem if you're using AGL, but still you might have a coding standard problem that keeps you on these old versions as well. Furthermore, you may have supply chain problems. If you are trying to pull in just random open source projects, those may not have the standards of sort of testing and certifiability that we expect from something like AGL. So you might not be able to get those to pass certification. So in any of these cases, we are trying to offer this fundamental C++ library that can solve these problems. The basic idea is that modern C++ allows us to do a lot of things that makes code safer and faster. And those are both really important in automotive development. And so it should be possible to use modern C++ in automotive development. And Arene makes this work. So a quick introduction to the team. These are the main developers of Arene Base. I'm a black hole on there, but you know. All of us are big C++ fans, and in fact, the four of us here with our names in red are all current or former members of the ISO C++ Standardization Committee. So we feel very strongly that modern C++ contains a lot of tools that are really useful for making code safer and faster at runtime. And we feel very strongly about people being able to use those in situations like automotive development where we believe it's the most useful. So I'm going to talk, just sort of quickly go through these three different themes here, basically. The major themes are standard library, and then additional things that are not part of standard library of C++, and finally a lot of things that we do for testing and safety, both for our code and for your code. So I'll just run through all of those in order. Starting with the standard library. So hopefully many people are familiar with C++ contains quite a large standard library. The C standard library is only a few functions, and you can actually, if you really wanted to do a hobby project, you could probably implement the entire C standard library in like a month, just working on the weekend or something. It's not that big. But the C++ standard library is a lot bigger and contains a lot of things that you would like to use in a basic C++ program. However, and unfortunately, many of those things that we use in the most modern C++ were only added in more recent versions. And so if you're stuck back on 14 or 17, you're missing some of these basic vocabulary types that we now take for granted in the most modern stuff. Things like span or string view. These are views into data owned by someone else, so it's kind of like a pointer, but it also knows Details about things like this current size is all packaged together, so it's a bit safer to use. It's also a bit easier to use at compile time. And then the next three, they're optional, variant, and expected, are basically type-safe unions. So they're unions that know what the current active type is. And these are very commonly used in the most modern C++, but they're not available until these more recent versions. So what we've provided from Arene is we've actually taken these and we've implemented them in C++ 14. So that if you're stuck on this old version of C++, you can just take these from our library and just use them exactly like you would use the ones from the more recent C++ versions. Except that they're even better for automotive use cases because they never throw exceptions and they never, well, these wouldn't do dynamic allocations anyway, but they don't do exceptions and they also have hardened precondition checks so that there's no undefined behavior, which also makes it easier to make a safety case about what they can do. Another thing that we have added is constexpr algorithms. So here's some code again. Apologies if you don't know what this means. I will go through very quickly. It's not too complicated. But basically the idea here is that maybe you have some message definitions. Maybe you have some definitions of like message types that can be sent around the car. And each one of these has a priority. And what this example here allows is to sort those messages by priority at compile time using normal code, no weird template tricks or anything like that. It just, you have this list of messages at compile time and all you're doing here is copying them and then sorting them using the message, the priority as a key. And these work exactly like the standard algorithms which operate on ranges of data, except that ours contains some features from future C++ versions where you can use them fully at compile time. And so this allows you to produce a list of all the messages that can be used on your ECU, sorted by priority, completely at compile time. There's no runtime overhead for this at all. Another neat feature that we have from future C++ is linear algebra. This is obviously a very big feature, so we're not going to provide everything here. But modern C, like C++ 23 and 26 provide quite a bit of support for linear algebra. So this is like matrices, vectors, addition, subtraction, multiplication, and then more complicated algorithms as well, like linear solve, LU factorization, this kind of thing. So what we are currently working on is backporting these to C++ 14 so that you get effectively exactly the API from C++ 26 in C++ 14. And the specific goal that we have here is to allow image processing in real time locally on a safety critical ECU. Which we think that we can do in just C++ 14. The key sort of secret sauce here is checking as much as possible at compile time and providing you with the nice syntax that makes it easy to specify things like the dimensions of matrices at compile time or ranges of data, that sort of thing. And this gives you both safety and performance basically for free. It makes your program compile a little slower, but the runtime overhead is basically nothing. So you might be hearing about all this, and if you are working in one of these safety critical ECUs and you sort of need these features, you might be thinking, okay, hold on, this is all really cool, but my environment is actually way more restricted than that. I don't even have a C++ 14 standard library in my environment. We have encountered a real environment where this is the case. Well, we have actually also implemented the C++ 14 standard library, just in case you do not have a safety certifiable version of the C++ 14 standard library. We have an implementation of that too. Not everything. So out of scope, all of this black stuff at the bottom is out of scope because it requires dynamic allocation or multi-threading. Because we are sort of imagining that you're using this in a environment where you can't use that stuff, because if you have a fully, a nice full OS like AGL, you have a standard library you can use. But if you're in this restricted environment where you don't have one, you probably can't do dynamic allocations either. So we've only implemented the parts that don't need it. But these top two categories basically are more or less completely available in our implementation. And this one below it, the third category, is stuff that we could implement if people come to us and say that we need it. The red one we probably will not do just because it's kind of not worth it, we think, but it could be done. And all of this is available basically at safety critical level. I'll talk in a little bit about how we do the safety evidence and stuff like that. So the next part is our own extensions, extra C++ features that we provide to your code. That's not, strictly speaking, part of the standard library or anything. The most popular of these by far is the inline containers. We have a bunch of these, and these are basically work like the standard containers. If you're familiar with C++, it has like a dynamic vector, dynamic double-ended queue, set, map, string. All of these perform dynamic allocations in order to hold the data, but they have a variable size within that, which is quite convenient. An array in C is obviously fixed size, and so you have to store the current size separately, and that can cause a lot of errors. So having this dynamically sized things are really nice, but the standard versions always do dynamic heap allocations, so you can't use them on some environments. So what we have provided is versions of these that have a set maximum capacity, and then they store that capacity on the stack or in a static variable, whichever one works better for you. And then within that, the current size can vary dynamically. So in this example, we have a fixed capacity of 25. And then we create a vector that is current size is 0, but the capacity is 25, and it's stored inside of the stack. Then we put new elements into it, just like we would with a standard vector. We put new elements in it one by one until it is full. And then we just do stuff on those elements until we're done with them. We pop them back one by one, and then the size returns back to 0. Again, just like you would with a stat vector. But during this whole time, there's no allocations. There's no APIs that can throw exceptions or anything like that. So this should be totally safe for a real-time, a hard real-time application to use. And so in addition to the simple vector here, we also have things like set and map and string, so that you can also have like these associative containers as well. The other sort of extension feature that I want to talk about is units and quantities. This is also a work in progress feature, but I think it's really relevant to automotive development, so I hope that people find it interesting. And if someone wants to use this, we would love to work on it some more, so please get in touch if this is useful to you. The idea here is that we are using compile time information to keep track of the units of specific physical quantity. Obviously, on a car, we are fundamentally controlling a physical object. So tons and tons of automotive applications deal with physical data like this, like the RPM of the engine, or how fast the car is going. Even stuff like the position of the seat in degrees, that's a physical quantity as well that has units attached to it. So we can keep track of that stuff at compile time, and then we can check when you try to add together two things, we can check if they are compatible with each other. If they're in the same units already, we just add them. If they're compatible but in different units, then we insert the conversion automatically to get it into the correct units. And if they are incompatible, then we make it a compile error and give you this error so that you can see what went wrong. So we get a combination of safety and potentially performance as well, because we can do all of this comparisons at we can do these unit comparisons at compile time only, and in the runtime code, the only part that makes it out is just like multiplication by this one common factor. So in this example here, we have a spacecraft. You might know that this is a real thing that happened, a real source of a bug that happened in Mars once. There's a spacecraft that keeps its current altitude in SI units, but there's a maneuver that someone has implemented that is implemented in US units. So it's giving feet instead of meters, basically. And in this first example, we are adding the current altitude, which is in meters, to the altitude gain from the maneuver, which is in feet. And our library is able to tell that those two don't match, or that those two are compatible but don't match, and apply the conversion automatically. However, if their underlying representation is in some type, like a fixed point type, where the information might be lost by doing the conversion, then we actually require you to write this in meter explicitly in order to say, I'm okay with the information loss, please do the conversion anyway. So that's an option as well. You can sort of push it through. But then if they are totally incompatible, for example, if you're trying to add the altitude with the impulse, which are two different things, then even if you include the cast to meter, it won't work, it won't match, and that will give you an error. So hopefully it's clear from this how this will prevent complete mistakes and also help you getting the right conversions when the things are compatible. So that's all the features that I want to talk about today. There's some other ones, of course, but you know, this is not a C++ conference. So instead, I should talk about safety and testing. So all of Arene, and especially Arene Base, the one that we are releasing yesterday, as implemented following ISO 26262, we produce all of the evidence that you need for this automatically in response to every single commit to the main branch. We have full AUTOSAR C++14 coverage. That's verified by static analysis. We have 100% line and branch coverage on basically every file. Not quite, but more or less every file. And currently we're at 85% MCDC coverage. We want to get that up to 100, but we haven't quite prioritized it yet. That's coming. So this basically any version of Arene Base is in this state always. So you can just pick it up and use it whenever you need. And if you need like the certification evidence, then talk to us and we can provide that as well. Also, in addition to these like common coverage metrics, we actually test. I mentioned that we never throw exceptions. Instead of throwing exceptions, we sometimes have these precondition checks that are effectively a panic, if you're familiar with that. So those can potentially cause the app to crash. If you're on a normal OS, like Linux, then a panic will cause your app to crash. And we actually check those crashes as well as part of our coverage to make sure that all of those actually crash when they're supposed to. And furthermore, I mentioned that we think compile time execution is really important. So we've made some Google test extensions here in order to check that compile time stuff actually runs at compile time, which can be a little tricky. So another nice thing that we provide from Arene is that those extensions. So if you're writing your own C++ code and you want to make sure that it works at compile time, you can use our Google test extensions in order to test that. So what we have here, the top one of these two examples is just a totally normal Google test case. This is the normal syntax where we just define the name of it and then you put some C++ code in there. It's effectively a function body. So you're, in this case, we have a compile time value, and then if you use the normal Google test assertion here, it only runs that at runtime, so it doesn't actually verify that your code works at compile time. On the other hand, if you use the built-in static assert, then you get a verification that it works at compile time, but not runtime. It doesn't give you the nice Google test output as well. And so it doesn't give you any test coverage. So the simplest way to do this test that I was talking about of testing compile time is to use these static assertion macros that we provide that basically just do both. So you get the coverage and you get the compile time check. However, we actually have a more powerful version of this that this probably doesn't mean much to you if you're not a C++ person, but so bear with me for just one moment. That if you use our constexpr test macro, then this makes the entire test body tested at compile time. And so you don't actually need to set each individual value to be a compile time value. You can write my type value here as a mutable value, and you can even mutate it as part of the test, and this test body is still executed at compile time, and it verifies that your code actually works at compile time. The only downside of this is the error messages are not as good as the Google test ones, but other than that, you get the compile time checks and you get the runtime test coverage without doing any weird stuff. Like, it's just a totally normal test body. Another neat testing feature we have, so probably some of you heard C++ and you're like, look, C++ is nice and all, but all of these templates and stuff are crazy. I can't test templates. There's like, you might test a template with type A, but then does the coverage even apply if you use the same template with type B? So what we have done with some of our tests, not all of them are like this, but some of our tests support providing a list of the specific types that you will use our templates with. So in this case of inline vector, your app maybe uses an inline vector with int32 and capacity 25. And if you provide that to us using this Arene instantiate tests macro, we will run our unit tests with your specific inline vector. So not the inline vector template, but the specific class that you are using. And we'll give you that full 100% test coverage on your class. And I think that anyone who's nervous about using C++ templates in a safety critical context, about getting certification for C++ templates, this should give you all the test coverage information that you need in order to get safety certification for it. And again, all you have to do this is, if it's a standard type that you're putting in there, you just write this type list and invoke the macro, and that's it. The coverage just comes out. If you have a custom type, like this non-copyable int, then you have to implement this function to tell us how to instantiate it. And that's all you have to do. So the last note I want to make here is that the specific platforms that we support here, we've tried to make this really portable. As I mentioned, a bunch of us are on the standardization committee, so we tried to just use standard features, no platform extensions, to as much as possible. So we're testing everything in the entire library using C++ 14 and 17, using our own standard library as well as the one that comes built in, GCC and Clang, and we mostly develop on Linux. Most of the platforms we target are Linux, but we also test it with macOS, and we even test it on a weird 32-bit ARM platform that doesn't have an OS at all. And all of these tests pass on all of these configurations. We run them all in CI, basically against every single commit to main. We use a lot of caching and Bazel and Nix and stuff to make this go fast enough to work. So if anyone wants to know about how we do the CI, please ask me about that too. I can talk about that. So yeah, that is pretty much it. A quick run through of, again, this is the first part of Arene. We hope to open source more parts of Arene in the future. But we think that this gives you the tools that you need to make your own C++ applications on basically any environment, and to get that safety certification that you need, whatever you're trying to work on. So there's the URL. Please give it a try. Send us an email. Open a GitHub issue if you don't like something. Yeah, we look forward to hearing from everyone. Thank you. If you have any questions, feel free to go ahead. ちなみに日本語でも大丈夫です。
So in this room is Asia, so it should be talk about English. But my feeling is Japanese are better, but I talk about English. So my first impression is excellent work in this one. But I have one question. So many person uses Rust same similar direction. So I want to know the strong point of this Arene Base from Rust environment.
So I think both modern C++ and Rust both have a lot of strong points. Obviously, in Rust, the strongest feature, in my opinion, is the borrow checker. So that prevents you from making these. It basically prevents you from making the so-called temporal memory safety errors, like the time-based memory safety errors, where you use something after you free it. Rust's, in C++, we do not have that. For sure, if that's a common error that you're seeing, then considering Rust probably makes a lot of sense. In my experience, in our real code at Woven by Toyota, we don't see very many of those use after free errors, in my experience. We see more, we do see out of bounds accesses sometimes, but those out of bounds accesses actually are covered by Arene Base. So spatial memory, like in Rust, they often talk about time memory safety, which is use after free, and space memory safety, which is out of bounds. And in space memory safety, if you use our Arene Base classes, we actually check for that. Now, as for the specific advantages that C++ gives you that Rust does not, a lot of what I've been talking about here is compile time checking, and things like the linear algebra compile time checking is really only possible with fancy template stuff. And in Rust, the compile time programming is quite a bit weaker than C++, in my opinion. So there's a lot of things, I'll get to Murata-san in a moment. There's a lot of things in Rust that must be done with macros that in C++ you can do with templates and with constexpr. That means that you can use more normal code. In Rust it has to be a macro, but in C++ it can be normal code. So I think they both have advantages. I hope they will both evolve in the future to be better. In the C++ committee, we are working on making C++ safer as well. So I think anyone who's considering making new software should consider both and compare the advantages.
Yeah, and also you should say that the Woven by Toyota is deeply involved with the safety Rust activities.
So yes, Woven by Toyota does encourage people to consider using Rust as well if they think that's a good option for them. Yes.
Do you have a plan to support the commercial version of ACL certified compilers and the utilities? Because you know, the most of the ACL D class of system is required to use this ACL certified compilers.
Yes. So as I mentioned, I think we're not going to be able to say, yes, we support all of them, because they're all different, basically. That's how it works. But I did mention that we have this ARM32 without an OS platform. This is specifically targeting one of those ASIL-D certified compilers. So our goal there is, part of our scope is that we do want this to be usable from ASIL-D using this like strange certified compiler. And in fact, many of those compilers do not have a standard library available, which is our original implementation for making our own standard library. The goal is to support ASIL-D. We'll see how well it works. Oh, and I guess I should mention that if someone has a special compiler that Arene Base does not work on, please tell us and we will try to make it work.
I have one question. If we use some backported standard C++ function from your library, and then if we want to port it to the other environment which has modern C++ library, what will be your recommend?
So I think in most cases, I would say it depends on your safety level. Mm-hmm. If you are in an environment where you really must not throw exceptions, for example, then it may be better to continue using the Arene Base version because it's not exactly the same. As I mentioned, some of the exceptions are replaced with panics in our case. So in that case, it may be better to continue using it. If you have more flexibility, then probably you can just go and, for example, replace this, well, like inline vectors are extension one. Replace things like Arene Base copy and Arene Base sort, just replace with std copy, std sort, it's the same.
Okay, thank you. And the other question is, how long are you going to support a C++ 14?
We don't have any, so the answer will be at least as long as we are using it. And currently, we have no plans to move on from C++ 14. I would like to, but I think at the very least, we should continue to support it as long as it is commonly used within the industry, because I think people who are on C++ 14 really need these extra features.
Yeah, makes sense. Thank you very much.
Anything else? All right.
It's on public now in GitHub, right?
Yes, it is public. The link, I'll post it again just in case anyone missed it. The QR code here does work. Okay, thank you, everybody.